Good morning and welcome to our lesson today on strip method of slab analysis. So strip method of slab analysis is a plastic method of stress analysis, and the different methods is accepted for analysis by Eurocode 2, and this include the method of plastic analysis. In our previous lesson, we did look at the yield line analysis of slab, and today we are going to look at the strip method of analysis, and both methods are plastic analysis. They are plastic method of analysis that we can use to analyze a reinforced concrete or steel slab. But why yield line analysis is an upper bound method, strip method of analysis is a lower bound method. And so what are the things that cause the development of strip method of analysis? The development of strip method of analysis was based on some disadvantages of yield line analysis, and those disadvantages include the fact that yield line analysis is an upper bound method. So if there is any form of error, it will be on the unsafe side, because the actual carrying capacity of the slab is less than or at best equal to the predicted capacity, so which is a cause for concern. And another disadvantage of yield line analysis was that when applying this method, it is necessary to assume that the distribution of the reinforcement is known over the whole slab. So you always will assume the distribution of the reinforcement and apply, then calculate the capacity. Another one is that it is a tool only for analyzing the capacity of a certain slab. You can't use it to do a normal slab, a normal design. You only will assume the rearrangement of reinforcement and then calculate the capacity. Another one is that you can probably use for design only in an iterative sense. That means for you to design, you place the reinforcement, arrangement of reinforcement, and then calculate the capacity. If that is okay, you're not okay, you come out with another arrangement. That is, you keep doing like this until you get to something that you're okay with. That is an iterative method, which is a kind of trial and error kind of design. And so these circumstances motivated Hillerburg in 1956 to develop what we now know as the strip method for slab design, which in contrast to yield line analysis, the strip method is a lower bound approach based on the satisfaction of equilibrium requirement everywhere in the slab. Being a lower bound approach means that it is safe. Every result you get from this method is safe, unlike the yield line method. And so these are the advantages of the strip method of analysis. It is just the opposite of the yield line. The strip method gives result on the safe side because it is a lower bound approach. The strip method is a design method by which the needed reinforcement can be calculated, not by iterative method like the other one. So now let's look at the basic principles behind the strip method of analysis. The governing equilibrium equation for this small slab, this is a small element of a slab, a 3D element of a slab, which is acted upon by a UDL of magnitude Q. So this is a UDL acting on this slab. This small portion of the slab has a dimension of dy dx. It has a dimension of what? Dy dx. And if you look at the slab, there is a moment. A moment in this axis is my. That is a moment in the y direction. And you have the moment here in the x direction. There is a moment in the x direction. There is a moment in the y direction. You also have a twisting moment. This moment that is put in xy direction. It is a twisting moment that is not completely in the x direction, not completely in the y direction. So you have this one. You also have shear force. This is the shear force in the vertical, in the YZ direction, shear force in the XZ direction. So this is the Y direction, this is the Z direction from this figure. So it is a slab element of dimension dx dy. So from this equation was generated that if you have the double partial differentiation of moment in the x direction with respect to x direction plus the double partial differentiation of moment in the y direction with respect to the y direction minus 2 times the double partial differentiation of the moment in the xy direction with respect to the xy direction. Now this is a twisting moment, so all this will be equal to minus q, where q is the UDL that is acting on top of the slab. The negative sign here is just to show that the moment is acting, the UDL is acting downward. And so these are the definition of the parameters. Q is external load per unit area, that is a UDL. Mx and y are the bending moment per unit width in the x and y direction. And mxy is the twisting moment. Now don't be overwhelmed by this equation. You are not going to do complex differentiation or integration, so don't be intimidated. But then, according to the lower bound theorem, so any combination of mx and my, which are the moment in the x direction and moment in the y direction, and the twisting moment that satisfy the equilibrium at all points in the slab that meets the boundary condition is a valid solution, provided that the reinforcement is placed to carry this moment. Now, it is not that complex to be overwhelmed. I'm going to break it down. So, but what makes life a little easier is the fact that we are going to look at the simple strip method. And the simple strip method assumes that the torsional moment, that is the twisting moment, is taken as 0. Of course, in a normal reinforced concrete design, we only have moment in the x direction, moment in the y direction. That is the main reinforcement and the distribution reinforcement. We don't usually have twisting moment. And so we assume that this twisting moment, mxy, is 0. So once you make that assumption, you can see the equation reduces to this. The component that had xy, this component is out. And so it makes life a little easier. The equation is reduced to this. Now furthermore, this equation can be split conveniently into 2 parts, and this representing the twistless beam strip action in the vertical direction and in the horizontal direction. So you can see this equation has been split. These 2 components, the component with mx and the component with my, has been separated. And how are they separated? They are just separated by introducing this component k. They brought this k here and 1 minus k. If you write k plus 1 minus k, it will give you 1. The answer will be 1. So actually, they are just bringing this concept to split. From this, you now have this as the x component and this as the y component. So what do we do with it? We can usually assume the value of k. And theoretically, we can assume any value for k between 0 and 1. And whatever value that we assume for this k, it will now distribute the load into the moment into the x component and the y component. Assuming now we say that the value of k is 0.5. If the value of k is 0.5, this component will be 0.5 q, while this component will be 1 minus 0.5, which is still 0.5. So you have 0.5 Q here and 0.5 Q here, which have distributed the moment equally into x direction and y direction. So let's also assume that we give k the value of 0. If we give k the value of 0, this component will be 0 because 0 multiplied by q is 0. And then this will be 1 minus 0, which is 1 times q. So we will have 0. The whole of this component will be 0, but the whole of this component will be q. That means all the movement will be in the y direction. There will be no movement in the x direction. So you can see that the value you assume for k will determine how movement is distributed into the x direction and y direction. So these are all the things that I've explained in this slide. So we can proceed. Now, these are also, like I said, theoretically the load Q can be divided arbitrarily into x and y direction. But the desired goal is to arrive at an arrangement of steel that is safe and economical and will avoid problems of service load level associated with excessive cracking or deflection. You don't want to pack all the reinforcement into one direction such that you start having cracking. And then the other side, you don't have enough reinforcement such that you start having a deflection issue. So now Hillard tried a number of load distribution that were not very satisfactory until he settled for the one described below. So in the next slide, we will look at the load distribution that Hillarbrook settled for after he has tried a number of them. So let's consider this figure. You have to look at it. Neglect this one now, neglect this one. Let's concentrate on this one. So if you look at this is a rectangular slab. This is a rectangular slab. This rectangular slab has this dimension A and this other dimension A. So that means it is a square slab of dimension A and dimension by A. So this dimension A, if you look at in this direction, we are dividing it into strip. This is actually where this method, the name strip analysis, comes from. So usually we divide a slab into what we call the edge strip and the middle strip. So for this side, this is the edge strip. In this x direction, this is the x direction, this is the y direction. So in this x direction, this is the edge strip, this is the edge strip, and it had a dimension of a over 4. That means 1 over 4 of that length. So this is from here to here is the middle strip, and the middle strip has dimension a over 2, while from here to here is the edge strip in this other end, and it has a dimension a over 4. So you can see now in this x direction, the slab has been divided into the edge strip and middle strip. So we have two edge strip, one at this edge, one at the other edge, and the middle strip. If you come to this y direction, the same thing happens. This is an edge strip with dimension a over 4. This is the middle strip with dimension a over 2. And this is another edge strip with dimension a over 4. So you can see the way load is being dimensioned. Now the next thing is the load distribution. Look at the load distribution. Let's start again at the x direction. In this x direction, look at the middle strip. This portion here, in this x direction, the middle strip here, there is no load. In this portion, all the load is in the vertical direction, that is the y direction. So that means in this horizontal x direction, the value of k was 0. So there is no load. All the load was in the y direction. Now look at here, you can see Q over 2 in this direction, Q over 2 in the horizontal direction. That means in the X direction, that means the value of Q in this place was 0.5, such that the load is distributed equally into the X direction and the Y direction. That means the X direction has the value Q over 2. The Y direction has a value Q over 2. And the same thing happened at this corner, Q over 2, Q over 2. If you come to this H strip, you also find the same thing. In the X direction, load is Q over 2. In the Y direction, the load is Q over 2. If you come here, the same is you have that in the X direction, Q was 0. There is no load in the X direction. But in this direction, Q is 1. That is Q. The corner has the same Q over 2, Q over 2, Q over 2. Now, if you come to this middle strip here, in the X direction, you have Q. In the Y direction, there is nothing. Q is 0. When you come to this middle strip, you have Q over 2, Q over 2. You come here, you have Q in this direction, and there is nothing in this direction. So you can see how the load is being distributed at different strips. So what you need to understand is how to divide a square slab into H strip and middle strip in both the X and Y direction, and how to distribute load in each of these strips. You need to do them. So if you look at the X direction here, or the H strip here, we cut a section AA. This section cut AA cuts at the H strip in the X direction. So what will they have at section AA? This is what they will have at section AA. What they will have here will be such that from here, if you move across from here, the value of Q at this place from here to here, H strip, is what? Q over 2. That is why you have Q over 2 here. But from here to here, in this direction, Q is 0. There is no load. That is why you don't have load here. At this H direction, Q is what? In this direction, Q is load is Q over 2. So you have Q over 2. So this is what you have this. This is how you have this. And so how do you calculate the moment capacity? It's just to come here. The moment, since this is this slab, did I mention that it's simply supported? It's simply supported, so you don't have any moment. You're not talking about support moment. All you're talking about is the span moment. So if you want to calculate the span moment, it's just to come and cut this thing at the middle and take moment. So all you need to do is to come here and take moment at the center. Cut this into 2 and take moment. You're going to see how we will do it when we are looking at the example. So if you take moment here, you're going to resolve this moment into a point load and place it somewhere and take moment based on this H. If you do that, you're going to have this QA squared over 64. You should try doing that. And if you come take moment again at BB, which is at the H strip, if you take moment at the H strip, this is what you will have, such that you will have from here to here, the value of the load distribution is Q. That's why you have Q here. From here to here, the load distribution is Q over 2. That's why you have Q over 2 here. And from here to here, the load distribution is Q. That is why you have Q here. So if you come here and divide this beam by half and change the load here into point load, remember changing to point load, you place it at this middle here, and also change the this one to point load and place it here and take moments all at this point. This is what you will have. You should try doing that. If you don't get it when we go into example, you will see. So this load distribution leads to practical arrangement of reinforcement, one with constant spacing, the one we are local. So this is at the H strip, that is section AA. This is what we have done. Mx will be equal to My because they are the both in the same. This is how they have taken the moment, I have just said. And in the YY direction, BB, section BB, this is how they took the moment. When we go to example, I think you will understand more. So now let's look at the example 1. The first exercise says that the 150 reinforced concrete slab is 8 meter by 8 meter and carries an unfactored variable load of 5 kilonewton per meter squared. The slab is simply supported in all the edges. Determine the moment at all the critical points in the slab, assuming the total load from partitions and finishes is 1.2 kilonewton per meter squared and unit weight of concrete is 25 kilonewton per meter cube. So we are going to solve this exercise. This is what we will do now.